In last lecture, we have already discussed about norm. Let us revise it. Norm. Let X be a linear space that is real or complex. Real or complex. Say R C. And this is a function from X to R such that it such that for all xy belongs to X and alpha belongs to R or C satisfies following conditions. Following conditions. First one, that is norm x is always greater than or equals to 0. Second, norm x is equals to 0, implied and implied by x is equals to 0. Third one and three, third condition of norm, that is norm of alpha x is equals to mod alpha norm x. And fourth one, it is norm of x plus y less or equals to norm x plus norm y. If all these conditions satisfied by this function, then this function is called norm. Then this function is called norm on x. Now, next definition is norm linear space. A linear space together with norm, we write it as x, thus is called norm linear space. This is a norm linear space. We have already discussed in last lecture. Norm is let X be a linear space that is real or complex, and this is a function from X to R such that for all xy belongs to X and alpha belongs to R or C satisfies following conditions. First condition is norm X is greater than or equals to 0. Second one is norm X is equals to 0 if and only if X is equals to 0. Third is norm of alpha X is equals to mod alpha norm X. And fourth condition is norm of x plus y less or equals to norm x plus y. Then this function is called norm on x. And norm linear space is a linear space together with the norm. Then ordered pair x norm, that is called norm linear space. In last lecture, we have already proved that one example. What is that? A norm on x, a norm here, a norm on x defines a metric D on x, defines a metric D on x, which is given by D of xy, that is equals to norm of x minus 1. This is for x comma y belongs to x. Means we have to show that this is a metric. This function defines a metric. Proof. We have already seen, but let us revise it. Just revise. First condition, we have to show that this function is a metric. Means there are three conditions. We have to satisfy these three conditions. First condition of metric. First one, metric, that is for x comma y belongs to x, then obviously x minus y also belongs to x, and x minus y belongs to x. By definition of norm, norm of x minus y is always greater than or equals to 0. But by definition we can write it is, that is d of xy is greater than or equals to 0 by definition. Norm of x minus y is d of xy. Okay. And this is nothing but the first condition of a metric. So this proves the first condition. Second one, d of xy is equals to 0. That implied y. X is equals to 1. This implies d of xy is what? Norm of x minus y. Norm of x minus y, that is equals to 0. But here again, norm of x minus y, we can write this as norm of x minus y equals to 0. That implied y, x minus y must be equals to 0. This is the second condition of norm. Then this implies x is equals to 1. Next is third condition. Third one is d of xy is equals to norm of x minus y. Here, norm of xy, norm of x minus y, add and subtract this norm of x minus z plus z minus y. This is again by third condition of norm. We can write this as norm of x minus z plus norm of z minus y. So norm of x minus z, we can write it is d of xz plus d of zy, and therefore d of xy less or equals to d of xz plus d of zy. That means d is a metric on x. D is a metric on x. Now, D is a metric on x. We can say that this norm is called the mid. We can say it is, this function is a metric induced by norm. You can say metric induced by norm. Next example is, say, for proving next theorem, we require this. So that is why we first prove this result, that is mod of norm of x minus y less or equals to norm of x minus y. Solution. As we know, norm x, that can be written as norm of x minus y plus 1. Add and subtract 1. Again apply second condition, norm of x minus y plus norm y. This is norm of x. Now this is here, that is less or equals to. Now this can be written, if we transfer this norm y in this side, that means norm of x less or equals to, here, norm of x minus norm of y less or equals to norm of x minus 1. call it as first one. And this is true. This is true for all x, y belongs to x. So replace x by y, x by y in 1 and y by x. So norm of y minus norm of x less or equals to norm of y. Say you can say norm of y minus x. But as we know, norm of y minus x and norm of x minus y are same. That means we can write norm of y minus norm of x less or equals to norm of x minus y, because norm x is greater than or equals to 0. As it is greater than or equals to 0, then there is no change. We call it as 2, inequality 2. From 1 and 2, as we know, if a is less or equals to b and minus a is also less or equals to b, so that obviously mod of a less or equals to b. So from 1 and 2, we can say that is, or if we write it is mod of norm x minus norm y less or equals to norm of x minus y. Means what we have shown here, we consider norm x, and that is add and subtract y. Norm x, as we know, by the property of norm, this is norm x minus y plus norm y. If we transfer in this side, we get this one. Interchanging x and y in 1. इंटरचेंज किए तो क्या होगा, नॉर्म y माइनस नॉर्म x इज लेस और इक्वल्स टू नॉर्म y माइनस x. Here norm y minus norm x less or equals to, we can replace y by y minus x by x minus y, because this norm function is always non-negative. So norm of y minus x is equals to norm of x minus y. And this one from 1 and 2, we say that अगर a less or equals to b है और minus a less or equals to b है, so we can write it is mod of a less or equals to b, means mod of this term, whatever it is, a. Here a means this complete term, no, or this term. अब यहाँ पे actually this is nothing but, if we take a common from these two, that is minus of norm x minus norm y, means it is a and this is minus a. So a less or equals to norm x minus 1 and minus a less or equals to norm x minus 1. So obviously this is mod of norm of x minus norm y less or equals to norm of x minus 1. This is the next result. Now second one, next result is, that is a norm is continuous. Prove that. Next result is here. So here, prove that norm is continuous. Now, what is the meaning of this norm is continuous? Continuity in function f is continuous. Function f is continuous. If limit x tends to x0, f of x is equals to f of x0. Say that is a single point. Here f means our norm. F means our norm. Means agar x, another meaning is x converges to norm x. X converges to, uh, we can see in the definition of metric. आपने प्रूव किया होगा कि एक्स डी एक मेट्रिक स्पेस है और वाई डी दूसरी मेट्रिक स्पेस है एंड टी इज मैपिंग फ्रॉम एक्स टू वाई. हियर टी इज कंटिन्यूअस. टी इज कंटिन्यूअस. कब कहेंगे टी कंटिन्यूअस है? इफ एक्स डी ऑफ एक्स वाई लेस देन डेल्टा implies distance t of x t of y less than epsilon. If we show this, then we can say this t is continuous. On the same line here in this case int t की जगह पे अपन norm लिखेंगे, norm, and we cannot write like this. So that means when prove that norm is continuous, that means when xn converges to x, another meaning is when xn converges to x here, actually the d of xy less than delta का मतलब है distance between x and y is less than delta, means distance between x and y is very small, then distance between t of x and t of y is also very small. In our definition, xn converges to x, means as xn approaches to x, then norm xn converges to norm x. That we have to show in this reason. Look. Here, let xn converges to x. Xn converges to x means limit n tends to. Now next result is prove that norm is continuous. Norm is continuous. Another meaning is x tends to norm x. Is continuous mapping of this x norm into R. This x norm into R means actually this is a mapping. This is a mapping. Means norm is continuous. This is a norm. Norm function is like this. For example, norm is a function from x to R. So if we operate norm on x, we get output norm x like this. So that's why here means we have to show that this norm is continuous. Norm is continuous means for example, as x, take one sequence xn, as xn converges to x, that implies norm xn converges to norm x. This we have to show. For this proof, and we have already proved that in metric. We already proved it. Say t is mapping from x to y. X and y are metrics. Metric space. D is a metric defined on x. D is a metric defined on y. This function here, t is a function. T is continuous if d of xy less than delta, means distance between x and y is very small, then distance between t of x comma t of y must be very small. Then we can say t is continuous function. We already proved, we already seen in a metric space. Here, instead of t, in this result, norm is there. Norm means distance between xn and x is very small, then distance between norm xn and norm x must be very small. That we have to show in this result. Now let X be a non-linear space and let X belongs to X. Xn be a sequence in X. And means consider that Xn converges to X. That is another meaning. Xn converges to X means limit Xn is equals to X. Limit Xn here. Limit Xn is equals to X as n tends to infinity. By definition, in non-linear space, definition is for n greater than or equals to n0 implies Xn minus X less than epsilon. Now we have mod of norm Xn minus norm X is less or equals to norm of Xn minus X. As we have seen, this norm Xn minus X is less than epsilon, so obviously this is less than epsilon. Therefore mod of norm Xn minus norm X less than epsilon means, another meaning, norm Xn converges to norm X. That means this norm function is continuous mapping. Therefore norm function is continuous. Norm is continuous. So okay, next result is that is a translation invariance. Translation invariance. The result is a metric B induces, theorem is a metric B induced by a norm on a norm space X satisfies first condition d of x plus a comma y plus a is equals to d of xy, and second one d of alpha x comma alpha y, that is equals to mod alpha d of xy, and this is true for all x, y, a belongs to x and every scalar alpha. Here that is very trivial, that is very easy. So, a metric D induced by norm means that is it, that we have already proved in previous theorem, previous example. What is that? D of xy is equals to norm of x minus y. This function is a metric induced by norm. It is a metric induced by norm, and this satisfies these two conditions. Okay, let us take first one. D of x plus a comma y plus a is equals to d of xy is norm x minus 1. That is by previous example. D of x plus a comma y plus a, another meaning is norm of x plus e minus y plus e. This is equals to norm of x plus e minus y minus e. This and this will get cancelled, and that is equals to norm of x minus y. But as we know again, this norm of x minus y means d of xy. This proves the first part. Now second one. Second one is d of alpha x comma alpha y. By the definition, norm of alpha x minus alpha y. That is norm of alpha x minus y. This is the property second. Sorry, property 4. Fourth property of norm. What is that? Mod alpha norm of x minus y. And that is mod alpha e into norm of x minus y is nothing but a norm of x minus y is d of xy. That is d of xy. And this proves the result here also. Now, next definition is another definition. It is here late. Next definition. Let X norm be a non-linear space. Let X norm be a non-linear space. Then x0 belongs to X if given epsilon greater than 0, there exists a positive integer m such that n greater than or equals to m implies mod of xn minus x less than epsilon. That means if xn converges to x, we write limit n tends to infinity, xn is equals to x as n tends to infinity. Now, next result is vector addition and scalar multiplication is jointly continuous. That is, if xn converges to x, yn converges to y, alpha n converges to alpha, then xn plus yn that converges to x plus y, and alpha n xn here alpha n xn converges to alpha x. Let xn converges to x, yn converges to y, and alpha n converges to alpha. These results you have already proved in third year also. Now, another meaning is that is limit xn is equals to x as n tends to limit yn is equals to y, and limit alpha n is equals to alpha. First condition is xn plus yn that converges to x plus y. So for this, limit xn is equals to x. Another meaning is for every epsilon by 2 greater than 0, there exists n0 belongs to n such that n0 greater than or equals to n, say n greater than or equals to n0, so implies norm of xn minus x less or equals to less than epsilon by 2. Also, second one, limit yn is equals to 1 means for every epsilon by 2 greater than 0, there exists n1 belongs to n such that n greater than or equals to n1 implies norm of yn minus y less than epsilon by 2. What we have to show? Xn plus yn converges to x plus y. Xn plus yn converges to x plus y. That means consider norm of xn plus yn minus x plus y. That is equals to, we can write this as norm of xn plus yn minus x minus y. Here that can be written as xn minus x plus yn minus y. From these two, this less or equals to norm xn minus x plus norm yn minus y. And now consider here take n, that is maximum of n, n, that is maximum of n0 comma n. For this n, or say n2, take n2 is the maximum of n0 and n1, so that n2 n is greater than or equals to n2 implies norm of xn minus x less than epsilon by 2 and norm of yn minus y less than epsilon. Now we have this one. This is the value of norm of xn plus yn minus x plus y. This is less or equals to norm xn minus x plus norm yn minus y. As we know, this value is less than epsilon by 2. This value is also less than epsilon by 2. This is less than epsilon by 2 and plus this is less than epsilon. This epsilon by 2 plus epsilon by 2 is epsilon. Now here again therefore norm xn plus yn minus x plus y less than epsilon for n greater than or equals to n. Another meaning is limit xn plus yn is equals to x plus y, means addition of these two sequences, that is also converges in non-linear space. Okay.